just adjust it a little bit. Okay, so hi everyone. My name is Di. I'm a PhD candidate at New York University. And my topic today is proactive safety monitoring, a functional approach to detect safety-related anomalies using unmanned aerial vehicle video data. I know this title is a little bit long. I will break it down for you when we get into it. But before we start, let's just quickly look at some statistics. As you can see on this slide, millions and millions of people are either injured or killed every year around the world by traffic crashes. Me personally, I found these numbers very, astonishing. And among all these, transportation road facilities, specifically for signalized intersections, they are among the most dangerous locations in the traffic road network. As you can see here, in the U.S. alone, about 1/4 of the road fatalities occurred at signalized intersections, and 1/3 of that occurred at signalized intersections. So in this study, we will be mainly focusing on the signalized intersections. And traditionally, people often use the police-reported crash data to evaluate transportation safety. Of course, including signalized intersections. Here on the left, I listed some of the example use cases how we can use crash for safety analysis. So, such as we can identify crash risk factors and high-risk locations, and after that, we can develop some sort of safety-related countermeasures. And then we can evaluate whether or not this countermeasures, works by conducting some sort of, before-after evaluations. But even though crash data has a lot of merits, it also has some limitations, which are listed on the right. As you can see, the first one is the long data collection time, which is due to the rareness of the crashes. And the second one is that less severe crashes are likely to get underreported to the police. And then thirdly, crash-based approach is often regarded as a reactive approach, which means that we need to accumulate a large number of crashes before we can do any safety evaluation. So in other words, this means that we're basically waiting for people to get injured or killed before we can, evaluate the safety. Okay, so considering this, transportation safety researchers propose this so-called surrogate safety measures to identify traffic conflicts or potential near misses to evaluate transportation safety. So here at the end, I listed two typical traffic conflicts. On the left, we have this rear end conflict, and on the right, we have this crossing conflict. So though you can understand this as close calls. So yeah, near misses. And then, generally speaking, we often extract surrogate measures from the vehicle trajectories. And then after identify traffic conflict, traffic safety risk can thus be quantified using them. And then comparing to crash-based analysis, using these conflicts or near misses are a more proactive approach because we don't need to wait for crashes to happen before we can evaluate transportation safety. And traditionally, the collection of vehicle trajectories is relatively difficult or time-consuming, which sort of limit the use of the traffic conflicts for safety analysis. But luckily, in the era of smart cities, we have a variety of emerging technologies, such as the connected vehicles, smartphone sensors, and drones. So all these emerging technologies makes the collection of vehicle trajectory data much easier. And among all of these emerging technologies, I'd like to emphasize on the drone data for a little bit, because with the help of computer vision techniques that are recently developed, or is starting to develop very rapidly lately, we can extract detailed vehicle trajectories from the recorded videos. And not only that, the data we extracted from the drone recorded videos shows the population of all the vehicles, which means that all the vehicles that are passing through this location will get recorded. And then the result of this is that all the safety risk at this location can be quantified. So accordingly, using this drone recorded data are very suitable for the proactive safety monitoring. So specifically, we can detect potential safety related anomalies that may cause a high safety risk or even collisions. And then after detecting that, we can probably intervene and try to reduce the risk, or issuing some tickets to the drivers to reduce further collisions. Okay, so based on what I'm talking about up to this point, the study framework and the objective of this study is to use the drone recorded surveillance videos at signalized intersections for the purpose of proactive safety monitoring. And specifically, we will focus on detect safety-related anomalies. Okay, so currently, if you're just looking at this framework, there's one key piece missing right now, which is the methodology. So specifically, how to represent the safety risk as signalized intersections before we can just detect the safety-related anomalies. I think this is a key question that we need to answer. So in order to answer this question, I think the first thing we need to do is we need to look into literature and see what is going on right now. So as you can see in this table, I listed some of the typical data aggregation levels that are currently used in transportation safety literature for identifying safety risk at signalized intersection. You can see for the temporal data aggregation levels, we have hourly or several minutes or per cycle, and for the spatial data aggregation, we have the intersection level or the intersection approach level. Okay, so I think the question we need to ask ourselves after getting this information from the literature is that, are this data aggregation level detailed enough to capture the traffic conflict or the safety risks that are obtained from the surrogate safety measures? So in order to answer this question, I think we need to take a closer look at the characteristics of the safety risks or the traffic conflict. So I think as far as I'm concerned, I think two characteristics are very important to mention here. The first one is that traffic or safety risk may change with time within each signal cycle and for different traffic movement. So I think this is mostly true because we are looking at the signalized intersections, right? Due to these traffic control devices, there are reasons to believe that the risk may not be the same throughout the signal cycle, right? And then, for example, for one approach, we have different traffic movement, like the throughput or left turning or right turning, right? And then the safety risk, the pattern of the risk may not be the same across different types of traffic movements. And the second characteristics of the safety risk is that it's actually specifically for this study, is that the changes of the risk caused by safety-related anomalies would be instantaneous, and the length of the impact would be short. So let me explain what I mean by this. So think about it like that. You are driving towards an intersection, and then you are given the green signal. So right now, you are under the impression that you will go through this intersection without any disruption because you are given the right of way at the moment. So suppose right now, the vehicle in front of you just suddenly stops. So at this point, you need to take some very immediate or instantaneous evasive action in order to avoid a collision. And then after this little incident, if hopefully it didn't result in any collision, then because you are still given the green signal, the traffic will still trying to go through these intersections relatively quickly. So the traffic will resume to normal after a few seconds. So this is what I mean by this second characteristic. Okay, so based on this analysis, I think what we need to find is that we need a method that can first model the time series of safety risk within signal cycles and for different traffic movements. And this method should also be able to distinguish between normal risk series and abnormal risk series. Okay, so after making clear of these requirements in this study, we propose to use the functional data analysis approach for our analysis. Okay, so for those of you who are not familiar with the SDA approach, I provide a very typical and simple example on this slide. As you can see in the picture on the right, the x-axis are the 12 months from January to December, and the y-axis are the measured temperature in degrees Celsius. And then we have 4 curves on this picture, and each of them represent one weather station in Canada. So this is a very famous data set in the FDA field. I think it's called the Canada Weather Station. If you want to know more, please feel free to check out the references down below. Okay, so this is the typical type of data that FDA deals with. So specifically, the functional domain are very consistent across different functions. And then all these functions sort of measure the same thing. So in this case, they measure the temperature, right? So more formally, FDA is a branch of statistics that analyze the curves or surfaces or anything else over a continuum. And oftentimes, this continuum is the time. Right? So like the example shown on this slide. Okay, so after briefly talking about the SDA approach, so let me give you a little bit of preview of how to use the SDA approach to detect safety-related anomalies for the signalized intersection. So I mean, in this slide is meant to be a general introduction about the whole structure. I will talk specifically about each of these points later on. Okay, so suppose we are looking at a pre-timed signal intersection, which means that the signal lengths are fixed. So suppose the y-axis is the safety risk, and the x-axis is the time. And then these 2 points represents the start and the end of the green interval of the traffic movements that we are interested in. Okay, now we have determined the location, we have focus, we have a specific traffic movement focus. Now we collect the data, we extract the trajectories, we calculate the risk. Okay, so supposedly this is the risk pattern of the first green interval. And then, after watching the video, there is nothing weird or dangerous happening during this green interval. And supposedly this is the second, and this is the third, and so similarly, nothing dangerous happened during these 3 intervals. So because there's no anomalies, so the patterns of represented from these 3 curves can be set as the normal risk patterns. And so, for example, if for the 4th green interval something happened, like so for example, some anomalies occur at the beginning and at the end of this green interval. Okay, so because something happened, the pattern of this interval is the abnormal risk pattern. And then in FDA, we first need to model these curves using functions, and then FDA provide a way to distinguish the abnormal risk patterns from the normal risk patterns based on the magnitude and shape. And again, I will talk more about what do I mean by magnitude and shape and whatnot in the future. Okay, but this is the general idea of how do we use the FDA approach to detect safety-related anomalies. Okay, so now I think we can finally complete this study framework by finding the last piece of the puzzle, which is the functional data analysis. Since we are on this topic, let's continue looking at some specifics about the FDA approach. So for this study, we basically employed 2 steps in the FDA analysis. So I mean, there are a lot of tools in the FDA toolbox, but these are the 2 steps that we use for this study. The first one is the functional data smoothing. So basically, we smooth the discrete data that we observe from the field, and then we represent it as a function. So, and then this, because after representing in the functional form, we can, extract more statistics for further analysis, which leads to the second step, that is to extract some statistics. So specifically, they are called the functional outlier detection measures, specifically for the outlier detection perspective, the detection objective. Okay, so now let's look at the first step, the functional data smoothing. So in FDA, a function is generally represented by a linear combination of a set of basis functions. As you can see here in the math equation right here, this is a linear combination of several basis functions, and the C here are the coefficients. And then in this study, we used one type of the basis function system, which is called the B-spline system. So the B-spline basis system is often used to model the non-periodic data, so which is the case in this study. So basically, we extract the data and we didn't see any apparent periodicity in the data, and so that's why we use this B-spline basis function. And then after that, okay, so this is a very quick example of what I mean by this linear combination. So suppose we have 5 basis functions, and then if we have the coefficients, we can just multiply each of these functions, each basis function with coefficients, sum them up, we get the blue function curves. Okay, so now another very important thing to keep in mind about the traffic safety risk is that they are non-negative, right? Because we cannot have like negative traffic risk. So I think it is very important to account for the non-negativity of the safety risk. So I mean, in FDA, we generally do that by using the exponential function, like shown at the top. And then the next thing is to estimate the coefficient so that we can represent the discrete data points using functions. So, so in this study, we choose to use the so-called roughness penalized fitting criteria. So the reason why we use this one is that it can penalize the roughness of the curves. As you can see, this criteria is composed of two parts. The first part is actually just the traditional least square, and the second part is this is sort of a penalty term that represents the roughness of the curve. So I think we can intuitively understand it. You can see this is the second derivative of the function, and from calculus we know that second derivative actually represents the curvature of the function, right? And then if we want to penalize a little bit more, we just square it. And then if you want to account for the curvature of the whole function, we just calculate this integration. And then we multiply with some hyperparameter, sum it up with the least square, we have this criteria. And unlike any other, statistical learning method that we commonly use, I mean, this hyperparameter can be determined based on some sort of a cross-validation method. So in FDA, we often employ a method called the generalized cross-validation criterion. So in this study, we adopt that to determine the optimal lambda, the hyperparameter. Okay, so now let's look at the second step in the SDA approach, which is the functional outlier detection. Okay, so a little bit more formally, the outlier functions are generated by a random process with a different distribution than the vast majority of the curves. So this is actually from the probability theory perspective. But if you want to look at it from a practical application perspective, there are basically two types of functional outliers. So the first one is called the magnitude outliers. You can see with the picture on the right. So these two observations, you can let's assume they are the majority of the curves, and then you can see the observation 3 are way above it. So basically, the magnitude of observation 3 is very, very large than the rest of the curves. So this is a typical example of a magnitude outlier. And the second type is called the shape outlier. As you can see at the picture on the right, so the magnitude of observation 3 is not exactly much different from the rest of the majority of the curves, but you can see the shape of the observations 3 are different from the rest of the curve. So this is a typical example of the shape outlier. And to target each of these two types, we find two branches of functional outlier method that can do that. So I mean, again, there are so many other functional outlier measures out there, and I think this is a very fast evolving field, even in statistics. So I mean, if you're interested, there are always more measures to learn, I think. And so the first branch is called the functional depth. Okay, so to have some intuitive understanding of what it means, let's look at the curve on the right. So as you can see here, all these red curves in the middle, so they are within the center of this whole cluster of curves. So I mean, in functional terms, we can sort of visualize or think of them like the deepest curves, right? Because they are right in the middle. And then when we are moving towards the boundaries, the depth of the curves will decrease, and then for the top and the bottom two functions, they will be the sort of the shallowest curve for among all of these functional clusters. Okay, so this is an intuitive way of understanding the functional depth measure. You can see like a valley, the function in the center are at the bottom of the valley. And in this study, we employed 7 types of functional depth measure. So, for the sake of time, I will not get into the specifics of these 7 functional measures. But I mean, if you're interested, please feel free to check out our paper. I will have the information of the paper at the end. But generally speaking, each of them has its own strengths and weaknesses in terms of detecting functional outliers. Yes, and then you can see, based on the intuition of the functional depth that I explained just now, the first branch, the functional depth measures, are very suitable for detecting the magnitude type of outliers. Because if we, rank the curves based on the depth, the ones with the least functional depths are the ones that are just, way on top or way at the end. So they are typical magnitude type of outliers. And accordingly, a second branch will be are needed to deal with the shape type of outliers. And this second branch are, the metrics in the second branch are sort of, created based on the so-called robust principal component scores. So let me give you a little bit intuition. So in this type, only two measures are proposed. So that they are called the bivariate score depth and the bivariate score density. So what does it mean by that? So it's like this. So we have a lot of functions, and then we apply this robust principal component scores method to get the principal component scores. And now we look at the space, the two-dimensional space created by the first two component scores, as you can see in the picture on the right. Okay, so we are sort of within this space right now. So for the first method, we calculate the two keys half space depth within this space among all the points. And then the second method is just calculate the kernel density of all the points within this two-dimensional space. Okay, so this is what I mean by, they're based on the robust principal component scores. And you can see on the picture on the right, right here. So you can see the identified outliers, the colored ones. Yeah, so the magnitude of these outliers are not that much different from the rest of the curves, but you can see the shapes are a little bit different, right? Especially, you can see for the red one, right here, actually cross in the middle, but in the shape is a bit weird. Okay, so these are, the two types of functional outlier measures we employed and the overall structure for using the functional data analysis approach. Okay, so now we're gonna go over this box one by one to talk about each of the ingredients. So first, let's just look at the drone recorded surveillance videos. So specifically for this study, we recorded the data for a signalized intersection called the Flatbush Avenue Tillery Streets, which is very near the campus of our NYU engineering school. So I mean, as you can see, there's the location of the intersection, and then specifically for this study, we focused on the northbound throughput direction, as you can see, as highlighted in the picture right here. And then we recorded data in the morning peak period from 6 a.m. To 8 a.m. And then here are some pictures and videos about the drone data recording. So we fly this DJI Spark drone, and then these are the the data that the trajectories we extracted from the drone. So specifically because we need to change the batteries and then refly the drone. I mean, the length of the batteries are not that great for this specific zone that we use. So we are only able to record 1 hour of video approximately within this 2-hour morning peak period within 2 days. And so this is before the pandemic. So this is sort of representing some sort of a normality of traffic conditions. And then we extract the vehicle trajectories. So this service was actually provided by a company, a private company called the Data from Sky, and specifically the longitude and latitude, the speed, acceleration, the vehicle type are extracted from the from the videos. A very sample example are shown in the table down below. Okay, so now after talking about the drone recorded videos, let's talk about how to quantify the safety risk using the surrogate safety measures. Okay, so in this study, we employed a variant of the famous time exposed, time to collision measure. So this measure was originally proposed by Dr. Minnerham. You can see the reference down here. So this measure is very famous for how to say that, quantifying the total length of time that are exposed to dangerous or risk situations. And in this study, we modified it a little bit. So instead of getting the time, we are counting the number of time steps exposed to the safety risk. So basically, we're amplifying the magnitude a little bit. Okay, so this is the only thing that we did. And then, so suppose the number of time steps for each second is 10. So which means that the smallest time interval of the vehicle trajectory data is 0.1 second, which is commonly the case in the real world data that we collected. So that's why so this actually represents that we just count all the time steps for each second, like across all the vehicles like are in risk. And then to account for the exposure of the traffic volume, we divide the calculated NTT value by the number of vehicles at that second. So finally, the safety indicator used in this study for detecting safety-related anomalies is the NTAT ratio. And then we calculate this data at a second for each second. So basically, we're going to have a function, and the discrete observations are the risk for each second. And then let's look at some specifics about the signalized intersections that we used in this study. Okay, so on the top we have the detailed ring barrier diagram right here, and this is a relatively complicated intersection, just a little bit. But for this study, we specifically focus on the northbound throughput, which are highlighted in blue, as you can see in this ring barrier controller. And then, the length of this green interval is 53 seconds. So which means that the domain of all the functions is between 0 to 52. And after watching these videos and then processing the data, we identified 27 complete protected green intervals. So, and this means that the total number of functions for our analysis is 27. Okay, so now I believe, all the ingredients are sort of discussed within this study framework. So now let's finally look at the performance evaluation of the proactive safety monitoring. So in order to do this performance evaluation, we need to obtain, the ground truth, right? So we need to know whether or not this cycle, this green interval has anomalies so that we can evaluate whether our method can be able to predict it. So in this study, we also define some rules to identify the potential safety-related anomalies. And then we are focusing on a very typical signalized intersections with 2 directions and multiple lanes in each direction. And the principle we followed in this study is this. So we are looking for any driver actions that may disrupt the right-of-way indicated by the protected green signal. So like I briefly mentioned at the beginning, after giving the green signal, right? So you are given the right-of-way. You are under the impression you're going to drive without disruption. So if a disruption occurs at this moment, then the risk will start to increase and maybe lead to a collision. So the first type of the safety-related anomalies is that the vehicles commit dangerous or illegal lane-changing behavior. So suppose this direction are given the green signal, and then you can see, the gap between these 2 gray vehicles are not that large. But if the purple vehicle do this lane changing, then they're gonna increase some sort of a disruption to this normal traffic flow. And the second type is called the vehicle slowing down or stop unexpectedly or abruptly. So suppose this direction is given the green signal, and then if the purple vehicle just suddenly stops, so the green vehicle will need to take evasive actions to avoid a collision. And the third type actually comes from the crossing direction. So suppose the direction of the gray vehicle is given the green signal, and then if somehow there's some sort of a illegal turning vehicle or leftover vehicles or red light running vehicles that are trying to pass into the intersection, then the green vehicle will be forced to stop. Okay, so these are the 3 types of safety-related anomalies that we identified. And then, to get the ground truth, what we did is that we manually watching the videos that we recorded to identify, safety-related anomalies. And the anatomy of all these anomalies are shown on the picture on the right. So you can see we have 4 type 1s, 1 type 2, and 2 type 3s. So which result in a total of 7 safety-related anomalies out of the 27 green intervals. Okay, now in order to do the performance evaluation, we need to use some sort of a matrix. So because in this study we are identifying anomalies, so basically this we can treat it as a classification problem with 2 classes. So in statistical learning, genre or terminology. So commonly used performance metrics such as the receiver operating characteristics, the precision recall curves, as well as the area under the curves of these 2 curves can be used as performance metrics to evaluate the results of this classification problem. Okay, so now let's look at some results. So first of all, these are the results from the first step of the SDA approach, which is smoothing the data. As you can see, the smoothed the data are shown on picture on the right, and then the outliers are colored in blue, and the normal curves are colored in red. And just by eyeballing it, we can see that there's a distinct separation between these outliers and the normal curves, right? And we can also see something interesting. So we can see that among all these normal curves, there are, some peaks at the beginning of the green interval. So I think, this is very interesting to me. So I want to understand what is going on. So after watching the video, we observed that there are actually some early acceleration of vehicles in the queue before the vehicles in the front accelerate. So I guess those drivers are in a hurry and try to, passing through this intersection as fast as possible. So if we aggregate the data, like what we did in literature, for example, we count the number of conflicts per cycle, and then if we, for example, like count the number of conflicts per hour, this pattern will not be revealed to us, right? So only after like we model this the time series of the risk can we reveal this type of new safety patterns. And then, okay, so I talked about the safety risk and the indicator previously, but what I didn't mention is the threshold that we use to distinguish between normal and dangerous, right? So, if we want to use the surrogate safety measures, I think we need to set some sort of a threshold. And, based on my personal experience, the threshold can make a difference. And sometimes the impact to the results are a lot. So I think it is of good practice to always, try to do this sort of sensitivity analysis on the threshold to get an understanding of what is going on and how the performance will change with different thresholds. So in this study, we propose to determine the optimal TTC threshold to be the one that achieves the best separation between abnormal and normal functional curves. So basically, we're because in the objective of this study is to try to achieve a good separation, right? So we're just trying to find the best TTC threshold that can do that for us. And specifically, we focus on the one outlier detection measures called as the acronym is the KFSD. This is the best measure. So I haven't shown the comparison of the different measures yet. I will show it in the next slide, but bear with me here and trust me, this is the best one. So we're going to use this one to determine the optimal TTC threshold. And the AUC value, the area under the curve for both of these two curves are shown in the table down below. And specifically, we tested 6 TTC threshold from 1.5 to 4 seconds. And then you can see if you look at the AUC of the ROC curve, the highest number is 0.88, which corresponds to 2.5 seconds threshold. And if you look at the AUC of the PR curve, the highest number is 0.8, which corresponds to the 3 second TTC threshold. So, this is a little bit inconsistent here, but if you look at the drop from 0.8 to 0.71, the drop is like 0.09, and the drop from 0.88 to 0.85 is like 0.04. So we'll go with the a 3 second here because it results in the last drop of the performances. Okay, so that's how we determine the optimal TTC threshold to be 3. Okay, so now let's look at the comparisons of different outlier detection measures. As you can see, we have 7 depth measures, like I showed. These are the 7 depth measures. These are the 2 of the measures that focus on the robust principles score. Okay, so as you can see, these are the ROC and the PR curves. So very quickly, the RO, if you were the better the performance, if the curves are in the upper left of the ROC curve, the better the performance. And if the curves are more in the upper right corner of the PR curve, then the better the performance. So just by eyeballing these 2 types of curves, we can see that there's some good of separations between the outliers and non-outliers. But in order to quantitatively understand the separation performance, we need to look at the AUC values, right? The area under the curve. As you can see, these are the AUC values for both of these 2 curves across the 9 measures that we tested. So as you can see, the KFSD measure achieves the best performances for both of these 2 curves. That's why we use the KFSD measure to get the optimal threshold. And then another good news is that the best results is pretty consistent, right? The KFSD achieved the best result for both of these 2 curves. And then another interesting observation is that we can see the first 7 measure, which is from FMD to KFSD, achieves a generally better performances than the last 2 measures. So if you recall, the first 7 measures correspond to the functional depth measure, right? And the last 2 focus on, the shape of the outlier. So this means that the safety risk functions caused by the safety anomalies mostly correspond to the magnitude type of functional outliers, not the shape type of outliers. Okay, I think this is another interesting observation here. Okay, so now I think up until this point, we have shown that the functional data analysis approach can actually achieve a good separation between normal curves and abnormal curves. And then I think the next thing we need to think about is that how can we implement this approach practically, right, in the field. So I think this is a sort of a tentative steps that I think we can use in the future or in practice. So first of all, we're gonna collect, the real data feeds from the drones, or of course for the street level traffic cameras, like shown right here. And then secondly, we need to extract the trajectories and then get the safety risk functions, basically something to get the new functions for the new signal cycle. And then, of course, we need to look for the pool that stored all the historically identified normal risk functions as a comparison. So if we put all of this together, we can calculate the outlier detection measures, right? So each of them will have a specific statistics assigned with them. And then maybe we can rank them up from the first to the last. And then, finally, we can set some sort of threshold to identify whether or not, the newly combed functions are threshold or not. I think these thresholds can be set based on the available resources for the agency and or some other factors. Okay, so here are some quick summary and some take-home messages. So in this study, we proposed a novel functional approach for detecting safety-related anomalies, and specifically, we propose to model the traffic safety risk as time series within each signal cycle, or more specifically within each green interval. And then, the proposed method can separate a normal risk series and abnormal risk series that caused by the safety-related anomalies. And we also defined some general rules to identify the safety-related anomalies for the case, so that we can get the ground truth, and then we can evaluate our performances. And we also summarized and compared 9 commonly used functional anomaly detection measures. And then, we found out that, generally speaking, good separations are found between anomalies and, non-anomalies. Okay, so now I think these are all the things I want to talk about for this specific research. But before we end our presentation, I think it is necessary or interesting to look at the future of the application of the SDA in transportation safety. So let me be completely clear here. So to the best of my knowledge, I think this work is the first one that applied the SDA in transportation safety. I mean, if any of you find any other papers that apply SDA in safety, please let me know, send me an email. I'm very happy to learn that. But since, if this is the first or some early works, I think it's important to think about the future of applying SDA approach in transportation safety. So, as far as I'm concerned, I can think of, the following 3 potential use cases of SDA in transportation safety. So the first one is to, facilitate proactive safety management for signalized intersections. So, because, right now, we are targeting like more detailed aspects of these intersections. So we are focusing on each specific traffic movements, and we are focusing on each specific second or time point, right? So if we found something weird happening, and then we can just immediately issue some sort of a targeted warnings or maybe some other targeted, intervention to reduce the risk. And the second thing I think is worth mentioning is the calibration of macro simulation model for safety evaluation. So, in transportation safety, a large part of the field are focusing on using the micro simulation models to evaluate the safety of a specific change the system, which probably cannot be done in the field, right? So, it is very necessary to first calibrate the macro simulation model before doing the evaluation, so that we know the model can represent the real world situations, right? So currently in the literature, people often use some sort of an aggregated measure, like the conflict counts or a distribution when during this calibration process. But I think maybe we can use these functions that we obtain from the field to calibrate the transportation safety. And then thirdly, very similarly, is to use the functional idea to determine the optimal signal timing in account for transportation safety. So again, in literature, people often use this sort of aggregated conflict count or sum of the risk and put that into the objective function when they are optimizing the signal timing. But here, maybe we can just use the functional idea, to maybe calculate the distance between two functions and put that in objective function so that we can represent, we can account for the time series, the whole structure of the safety, instead of using the aggregated value. And then also, finally, I'd like to mention some, open questions. I mean, just to be honest here, I don't actually have answers for them. I'm still trying to understand, but I think these are some good questions that I need to think, or for the future, to think about how to use FDA for transportation safety. So first of all, is that can we adapt the method I proposed in this study to the adaptive signal control? I think I mean, even though the fixed time or pre-time signal control mode is still probably the majority of all the signal control signalized intersection in the world, but I think gradually people are sort of shifting to this adaptive signal control. So can we, apply FDA here? Because in this study, when the signal timing are fixed, what is nice about this is that the domain of the function is the same across different functions, right? But if the signal keeps changing, the domain of the functions will keep changing. So will that, work? Can we still apply the FDA? The second thing is that in this study, we applied the FDA for the signalized intersection, right? So I mean, again, very nicely, the signal control devices provide a natural cutting point that could start at the end of the green interval. So we can just cut the traffic safety risk into little pieces and then put them together as functions. But what about for any other uninterrupted traffic flow, like the highways? Can we still, I mean, I think in theory we can do that. We can just manually cut them into pieces and do that, but it still work? I think that's a question for the future. And then also it's about the transportability. So, I mean, again, we look at the one specific intersection and for 1 hour data that we collected and in a morning peak period. But what about in different types of times of day, like night or evening? And then what about other intersections in other cities or countries? And can this method still be used, for other places? I think this is also some interesting research questions in the future. And then, with that, before we start the presentation, let me acknowledge my collaborators, my supervisor, Dr. Kai Nosbe, and two of my seniors, Dr. Quincy and Dr. Hong Yang from Old Dominion University, and two of my colleagues from NYU, Fanzo and Disha. And then, and this study was also partially supported by the C2 Smart UTC at NYU. And we would also like to thank the Data from Sky for extracting the vehicle trajectories for us from the drone recorded videos. And then for those of you who are interested in knowing more about what I just talked about, so for the sake of time, I didn't get into the mathematics, the specifics about each of these traffic functional outlier measures that I used in this study. And for example, if you want to know more about the performance evaluation and anything else, please feel free to check out our paper. The title of the paper is the same as the title of my presentation, so feel free to Google it or send me an email and I can just send you. And with that, I'm gonna stop right here. Thank you so much for listening, and any questions are welcome.
Dee, thank you so much. This is really interesting research. I copied and pasted for everyone interested. I copied and pasted the title of the paper and the link in the chat. So I'd encourage attendees to ask questions one of two ways, either by using the Q&A box, if you already have a couple of questions, or by raising your hand, and I'll find you and I'll call on you and you'll be able to ask the questions directly to Dee. So the first question that has come in here, Dee, is how did you decide the number of the spline group? Does the number affect anomaly detection?
Right. Okay, so this is a good question. So in this study, so I have an extra slide right here. So I mean, in the original slide, I didn't put this part in, but here in this study, we sort of constructed the B-spline system in this way. So we first, so this is sort of a convention in the FDA field, I think. So we first divide the functional domain into a small number of subintervals, and oftentimes people, set the subinterval, the cutoff point of intervals as the same as the observed discrete values, observations, right? And then we follow this convention in the study. And secondly, we set the order of the polynomial for each for these the B-spline system to be 4. So we tested several different orders, but I think this is sufficient enough to represent. And after setting these two, we can actually compute the number of basis functions. So I think there's an equation there. I mean, if you want to know more, send me an email. I think there's an equation that are in the book. In this book, right here. Yeah, so in this book down here, they have an equation of calculating the sufficient number of basis functions used to specify the functional space. Yeah, I hope that's answered your question. But yeah, feel free to send me an email. I can send you more materials on this.
Okay, so Dr. Osby asked if you could elaborate more on the advantage of using a continuous function rather than count data for the anomaly detection. Why using functions is a better approach?
Yeah, so this is a great question. So right. So why we need to smooth the functions into continuous curves? So because in some of the functional outlier measures, or maybe for filter analysis, we can use some other tools in the FDA toolbox. But anyways, all these measures are sometimes required to calculate some sort of derivatives, or some other measures that are best to be computed using a continuous functional form, right? So because in the discrete data, when we are calculating the derivatives, we maybe use this very delta t, and then just between each two pair of points. But then we may miss some information, or this curve may not be smooth enough. But if we convert it into the continuous function, then a lot of more analysis can be done, like the derivatives, or so basically we now have a functional form that we can work with, and we can calculate all different types of things, like what we did in calculus or some other field that we learned previously. Yeah, thank you for the question.
Jenny asked, what's the computational time of this approach if deployed in real time?
Yeah, so right, I think this is a very interesting, good question. So I think I mentioned like a tentative approach if we want to apply this method in the real world. I think like this, yeah. So the first step is, of course, we need to extract the data, the trajectories from the videos. I think, currently, if we just, for example, if we have the real-time data feed, like for example, we have a 1 minute video, I think maybe we can just extract the trajectory from a relatively fast manner. And then after that, everything else are just, computer codes, right? Just calculate the functions, smooth it, and compare and calculate, and then rank. So I think the most computational effort should be spent on sending and transmitting the data, and then extract the trajectories and that. But I think since we are maybe monitoring this from a real-time perspective, and the data that we transmitted are maybe not that large, like several hours, just maybe several seconds, I think we should probably be able to do it in a relatively near real-time mode. In practice. Yeah, thank you for the question.
So another one, what are some, what kind of performance improvements might this approach bring to signal timing optimization? Maybe it's too early to tell.
Oh yeah, this is a good question. So the honest answer is I don't know, because I think this is one of the future research. But as far as I think about is like this. So if we aggregate the data, we get the count for each cycle. I think there are some papers in literature that count the number of conflicts for each cycle, and then we're gonna update the next several cycles, the signal timing of the next several cycles. So so instead of using the count, if we use the time series of the functional curves, so basically you are asking what is the difference in that. So what will be the difference if we use just the one number, the count number, and the function? So I think this lies, the characteristics of the traffic risk of the specific intersection, I think. So if, for example, 2 cycle has the same count but has two different types of time series curves. Like, for example, the first one is have a bump at the beginning, and this next cycle have a bump at the end. Then if we count the number of conflicts, we may not be able to see the differences, and the algorithm may not be able to update based on that. But if we use the functional idea, and then use some sort of a distance measure and whatnot, we can maybe reflect these differences between the two cycles, and then we can do something to optimize the signal control time. Yeah, this is what I'm, as far as I'm concerned. But this is a great question. I think it is worth more time and effort to look into it. Thank you.
When you were proposing the rules for identifying safety-related anomalies, what are some additional rules that you might have considered, or modifications to the rules that you proposed?
Yeah, this is definitely a good question. So let me just put out a slide for you. Okay, so here we identified 3 types. And so, so I think let me explain a little bit more how we come up with these rules. So basically, we're just, first of all, we're just watching the videos, and then after watching that, I saw some sort of just very risky behaviors from the drivers. So it got me thinking, how can we determine some sort of a general rules that can apply maybe to a more broader perspective. So that got me thinking, like we need to look for the right of way for a specific road facility. So in the signalized intersection, the right of way are clearly indicated by the green signal, right? So basically, if this approach is given the right of the green signal, then they have the right of way, the absolute right of way right here. So this means that nothing should interrupt it, because they have the high priority right now. But so if something disrupts that, then they will result in high risk. So I think the way of looking at the right of way, searching for the right of way before identifying the safety anomalies, can be some sort of a general rule to be applied to other road facilities. So for example, if you look at the highway, if there's a sort of a run metering control right here, and then if the run metering has a signal control or something like that, and then if it's given a green signal, and then maybe they have the higher right of way. The highway may not have that, but maybe the highway have the right of way for different circumstances. But I think if we know the right of way at the moment, I think we can try to find some weird or dangerous actions that can disrupt that, which may result in a potential safety-related anomalies. And I hope that answers your question.
Yeah, that was great. And we have time for this last question, which is quite large. So let me see if I can break this apart appropriately. Assuming that you can obtain trajectory data continuously from drone or via other techniques, can you just elaborate even further on some implications on the proposed approach for proactive safety management? You mentioned a couple of different options. I guess the question is asking you if you could elaborate a little further, or if you had other ideas that were not in the slides.
Okay, so yes, right. So if we have continuous feed of the data, I mean, of course, we can use the method I proposed. The method proposed here. So for example, if we have the continuous data feed, right, and then we can extract the trajectories, and then we can calculate the risk and then identify the conflicts. So, but if you want to look for some other method, I think an easier way would be to just using the things that people are often doing in literature. Basically, we can just count the number of conflicts, right, for each cycle for green turbo, and then we can rank the count simply to identify the conflicts. So I think this is one of the most easy ways to do that, instead of accounting for the whole safety risk. Another thing is that maybe we can use some other summary statistics, like maybe we, instead of focusing on the green turbo, we can focus on the whole cycle. Maybe something happened during the red interval. We don't know, right? Because if the vehicle just approaching the direct, maybe they have some sort of a dilemma zone or whatnot. Maybe we can look at some other perspective of the intersection to look for more implications. Right?
Yeah, that was the second part of the question. It was about looking at the red light intervals as well, and perhaps identifying such instances like abnormal rear end conflicts. Yes, so this also reminds me, we're at Teaching Smart, we're dealing with cities, but I think there was some research going on out of UW in partnership with Microsoft about identifying near miss collisions and how that would drive infrastructure investments, particularly on highways that are like where people can't anticipate certain turns on highways or where ice accumulates on certain sections of highways. I thought that was a very interesting connection to this research as well.
Yeah, definitely. Yeah, thank you, John, for mentioning. So I think, this is a really good point. So in this study, we focus on green interval, but what if something happened during a red interval or during the yellow phase, right? So of course, we can definitely do that. And so this method, we can, if we increase basically the domain of the function a little bit to include the yellow or the all red term or for the whole red period, and then we can also still model all these risks as functions, and then we can still apply the same method to see if there's something weird going on. All right, thank you.
Okay, so that was the last question. I think we're out of time. Huge thank you to Dee Yang. I put the paper in the chat and I'll send it out via email. As Dee mentioned, this webinar is sponsored by, at least partially by the CP Smart Center and USDOT. Dee, thanks again.
Right, thank you, John. And thank you everyone for listening.